So for instance, in a plane, we know that a plane is a two-dimensional system that is there. So when I tell two-dimension, we generally have x, y axis. So what we can do right now is we can find the position, the velocity, and the acceleration also. Now, how are we going to do this? For this, we need an xy axis. So assume this point is P. So I can draw a position vector to this particular point, and let's say I can call this as R1 vector that is there. So for this point P, I have the position vector R1. Now let us assume that this point was moving along this yellow path that I have given. So in order to understand, what we will do is we will just label the axis, because without labeling the axis we don't know what we are actually doing. So x and y we have, and R1 gives the position vector of point P along this path. Now at a later time, if I want to find the position of this vector, let's say this point at this blue mark that I have put, I will draw another position vector here. So this would be written as R2 vector. And since we are talking about vectors, if we are going to put our directions like this, we know that the resultant should be in the opposite order. Now whichever direction we want. Ideally speaking, the particle has to move forward. So this point P is moving forward. So therefore my resultant, I will draw it from R1 to R2. So this is going to be my resultant vector in this direction, and I will simply write this as delta R, because I need to know by how much R1 has moved to R2. So that is the difference that is there that I will get from this particular expression. That is, delta R is equal to R2 minus R1. Now in order to understand this a little better, what we can do is we can go ahead and drop the perpendiculars onto the x and y axis, so we can define what is the R1 and R2. In the sense, R1 vectors, if I take all of this as vectors, R1 vector would be nothing but x1 I cap plus y1 j cap. Similarly, R2 vector would be x2 I cap plus y2 j cap. Now I need x1, x2, y1, y2. Now for this particular position here, so I'll take a very thin line and I will draw it such that this will give me my x1 and x2. So this is going to be x1, this is going to be x2. Similarly to the y-axis, if I'm going to draw it, from this point I would get my y1, and from here I would get my y2. So y1, y2. Now always remember, since you are doing a construction here, an extra from what is given, always the perpendiculars are generally drawn as dotted lines. So we will go ahead and make sure that our lines are also dotted. Okay. So here you can see that I have got two positions. So x2 minus x1 would correspond to the difference in the position. That would give me delta x here. And similarly, this would give me delta y, the difference between y2 and y1. So let us go ahead and rewrite this expression. Since we have done addition of vectors analytically, it is going to be a little easy. So I have had delta r vector is nothing but r2 vector minus r1 vector. So the difference in the position is what I'm getting here. This would be nothing but x2 I cap plus y2 j cap minus x1 I cap plus y1 j cap. Now please remember to put the bracket here. Now as we have done previously, we will put all the I caps and j caps together. So I will have x2 I cap as it is. Now y2, when it goes here, it is going to be y2, and x1 will have a minus, y1 will have a minus, that is there, and this is basically delta x I cap plus delta y j cap, which is nothing but our delta r vector that is there. So this would give us the change in position of the vector from the point P to, let's say, P prime. Delta r is the change that is there. Now how do we estimate velocity? We know that velocity as a vector is nothing but displacement by time. So this is the standard formula, or displacement we can write it as delta s by delta t, which is nothing but s2 minus s1 divided by t2 minus t1, where t2 is the time corresponding to s2, t1 is the time corresponding to s1. Now in our case, instead of delta s, we have it in terms of delta r in its component form, that is delta x I cap plus delta y j cap. We can do an algebraic sum here and divide this by delta t. This is allowed. So what will we end up getting? Delta r vector by delta t, which is nothing but our velocity, is equal to delta x by delta t. I will take it as vx I cap plus vy j cap, where I can write vx is nothing but delta x by delta t. Now we have done differentiation previously in order to solve a few problems. So keeping that idea in mind, here we can do the same thing. We will apply a limit such that delta t becomes small. Now the understanding of it physically is we want to cover the given distance in a very short amount of time. So that is why delta t tends to 0. Mathematically, when we do this, we get the expression dx by dt. So my vx, I can write it as dx by dt, and similarly vy can be written as dy by dt. So our final v vector could be written as dx by dt I cap plus dy by dt j cap, or vx I cap plus vy j cap. Now since we have already gone through of how to find the magnitude of v, let us do that. So the magnitude of v vector would be nothing but root of vx square plus vy square. This is in 2 dimension. For the expression v vector is equal to vx I cap plus vy j cap. Now the same thing if I want to do it in 3D. I could start with my r vector, or the delta r vector should be delta x I cap plus delta y j cap plus delta z k cap. Exact same thing. We are going to divide it by delta t, how we have done it previously. I will get it to be, this is equal to delta t. I am dividing all the coefficients of the 3 axes, that is x, y and z, delta x, delta y, delta z by delta t, and we will get velocity as, let's say, we will apply the limits also. Delta t tends to 0, delta r by delta t is equal to limit delta t tends to 0. Now since I'm applying limit for all the three, I will write it together. Delta x by delta t I cap plus delta y by delta t j cap plus delta z by delta t k cap. So our v vector can now be written as, in terms of limits if I'm writing, I can go ahead and write this as dx by dt I cap plus dy by dt j cap plus dz by dt k cap, or v vector is nothing but vx I cap plus vy j cap plus vz k cap. So this is how we do it in 3 dimensions. Now we would restrict velocity to only 2 dimensions because that is a little more easier for us when we use the position time graph. That is, if I have position versus time, velocity versus time. This expression that I have derived for 3 dimensions is mostly used in analytical method for numericals. So let us consider v vector is nothing but vx I cap plus vy j cap. Now we have done this process previously also to find the angle between two vectors. Which two vectors? Vx vector plus Vy vector. So if I take the two axes and if I'm going to put my vector here, this is my V vector, I will have this as Vx and this as Vy. This is Vx, this is Vy. Vy, Vx. And we have seen Vx vector is nothing but Vx I cap, Vy vector is Vy j cap. So let us go ahead and find the angle. Now this is the angle that is at theta. So this is going to be Vy. In terms of magnitudes, if I take, I will have tan theta is nothing but Vx, Vy, that is the opposite by the base. Vy by Vx, or theta is equal to tan inverse of Vy by Vx. Now this is easy to find. The angle is easy to find for 2 vectors. For 3 vectors, the process is a little more complex. So we will restrict ourselves to the simple fact of 2 vectors. Now we have seen position, we found the position vector, we have seen velocity, now, and we have also seen what are the components of velocity and how we have derived it. Now the last physical process that is remaining is acceleration. And acceleration, all of us know it to be nothing but delta V by delta t, or if I'm going to apply the limit, delta t tends to 0, delta V by delta t, this can be written as dV by dt. So let us proceed from this expression of delta V by delta t. So this is going to be nothing but delta by delta t of 2 dimensions. If we take, I have Vx I cap plus Vy j cap, which I can write it as delta Vx by delta t I cap plus delta V by delta t j cap, or A vector is nothing but Ax I cap plus Ay j cap, where Ax was nothing but delta Vx by delta t and Ay was delta Vy by delta t. Now in terms of limits also we know how to do it, right? So we can write A vector as, so here if I apply the limit for Ax, not the vector, just Ax, if I do, it is going to be limit delta Vx by delta t by the limit delta t tends to 0. This I will get it as dvx by dt. Similarly, ay, when I'm applying the limit delta t tends to 0, delta v by delta t. So this is ax. Ay will be dvy by dt. So if I have to write this entire expression in terms of 3 dimension, I can again go ahead and write a vector is equal to ax I cap plus ay j cap plus az k cap, which is dvx by dt I cap plus dvy by dt j cap plus dvz by dt k cap. But wait a minute, there's a catch here. We have dv by dt as nothing but, sorry, not dv by dt, the velocity as dx by dt. Correct? So we know that rate of change of displacement is velocity and rate of change of velocity is acceleration. So how do we incorporate this into this expression? Now for that, mathematically what we can do is, I'll take a simple example. If x is my displacement, the velocity will be written as dx by dt, and acceleration would be nothing but dv by dt, which we can go ahead and write acceleration is d by dt. Now what was v? Dx by dt. Now here please keep this in mind, d by dt is a function. It is not an algebraic expression, rather it is like a function, just like how we have sine, cos, tan, the trigonometric functions. This is a differential function. So acceleration can now be written as d square by dt square of x. That means you will differentiate displacement along the x-axis twice to find the acceleration along the x-axis. So I can go ahead and write acceleration to be, let's say, dvx by dt I cap plus dvy by dt j cap plus dvz by dt k cap, and this I can still write it as d square by dt square of x I cap plus d square by dt square of y j cap plus d square by dt square of z k cap. So we have actually done this previously when we have seen how differentiation works. And we've also plotted the graph in order to understand what happens. The slope becomes more and more flat or more and more parallel to the time axis. If I have, let's say, displacement versus time, velocity versus time, acceleration versus time, and we plotted these three in one of the previous videos, we would have seen how this slope would have changed. So from something like this to a flat line that is there. That is what differentiation is all about. Now these terminologies may look a little confusing, may be upsetting, but once we do few numericals, things will become a little easy. So let us look at motion in a plane with constant acceleration. Now for this, we can take the following case. When the time is equal to 0 seconds, the velocity of the body is going to be the initial velocity. Now initial velocity, we generally use the symbol u, or we can take it as v0. Both cases it is correct. And at some time is equal to t seconds, we will have the velocity to be the final velocity. So this is initial and this is the final velocity that is there. Now we are going to use this idea to find out what is the acceleration. Previously we have derived or we have defined acceleration in terms of velocity as well as displacement. So acceleration here would be nothing but v naught, that is the final velocity. So v minus v naught divided by t minus 0. So I get this as v minus v naught by t, which is nothing but the acceleration, the change in velocity with respect to the time that is there. Now, if I have to write this, so I can just rearrange this and I will get v is equal to v naught plus at. And I can go ahead and make sure that I can write velocity in terms of components, because this is a vector. These two are also vectors. Velocity and acceleration are vectors. So Vx would be nothing but Vox, that is the initial velocity, plus acceleration along the x-axis plus time, and Vy is going to be nothing but Voy plus Ay into t. Now note, time does not belong to any axis, so we cannot have tx and ty. Time is just being measured. For what? To understand what is the velocity and what is the acceleration. So if r and r naught will give us the position that is there at time t and 0 seconds. That means at the beginning, if I'm going to have position as 0 and the final position is r, this is the times that are measured. So I will get r minus r0 as nothing but v plus v0 by 2, which is nothing but the average velocity. So with a certain average velocity, the body is moving from position r naught to position r. Now let us go ahead and substitute for v, the expression that we have found. So what is it going to be? I will have r minus r naught is equal to v naught plus at times, is going to be a plus v naught whole divided by 2, or r minus r naught is equal to 2v naught plus at, or r minus r naught is, this is divided by 2, is equal to v naught plus half at. Now this equation resembles s is equal to ut plus half a t square. So since we are looking at the change of, let's say, the displacement in terms of velocity, we have to write a t here. The understanding is the change in, or the displacement is nothing but velocity into time. So this t comes here. Now this is equivalent to this. So what have I have here in terms of displacement? R minus R naught. Or I can go ahead and write my R is equal to R naught plus V naught t plus half a t square. In terms of its components, if we write, x will be nothing but x0 plus Vox into t plus half ax t square. This is the position along the x-axis. The position along the y-axis, y is equal to y0 plus Voy t plus half ay t square. So what is our understanding from this? For what did we go ahead and derive this expression? The first and the foremost thing that is there is, these equations are one-dimensional equations. That means for a motion in a plane, we can get two one-dimensional equations to represent its motion. Now here, this is the expression in 2D. But you can see that I have resolved it along x and y. So I've got two independent expressions along the x and the y axis. The second one is, these are simultaneous equations. So we can solve these as simultaneous equations provided the acceleration is uniform, not constant, but rather uniform. So only if the acceleration is uniform can we, let's say, divide, or can we simplify a two-dimensional motion equation into two separate one-dimensional equations and then solve them simultaneously.